Hello again, and in this video we're going to continue looking at how do we draw shear bending and axial force diagrams for something other than a simple beam, which is how many people are taught how to do these shear and bending moment diagrams, same with axial force. It's just with a simply supported beam, statically determinate, and so what we want to do is work with slightly more complicated structures because when we're as structural engineers, when we use these diagrams in order for us to have an understanding of what the demands are around a structure, and so that we can design them appropriately, our structures are going to be more complicated than just beams. And so what we're going to look at to start with is this simple frame. So you can see the frame is 6 meters wide at the bay, and it is 4 meters tall and just has 2-point loads applied there. And so what we need to do for this example is draw the shear, bending, and axial force diagrams for this frame. So the first thing that we need to do in order to do this is always just draw a free body diagram, find what our reaction forces are, and then everything will sort of fall out from there. So starting with that, our free body diagram of this little structure. We'll just draw her up here. And we'll put the loads on there. That's 30 kilonewtons and 30 kilonewtons. We have a pin on this side. We'll just call this side A, so we'll have a X and a Y, and we'll call this side BY, and no free body diagram is complete without some dimensions, and so that's 4 meters tall, and we have 2 meters, and 2 meters. Alright, well, now that we have a free body diagram, we can use our equations of equilibrium and we can solve for these reactions here. And we'll start with the sum of the forces in the X. So we'll go plus. And those forces equal 0. So if we look here, AX simply equals 0. So that's a nice, easy one to start with. Then we'll how about we sum moments about A, and that way we can isolate BY and only have to deal with one variable at a time. So the sum of moments about A equals 0, and so what do we have? We have a negative 30 kilonewtons times 2 meters, because it's spinning clockwise, minus another 30 kilonewtons times 4 meters, and then because BY is going counterclockwise, we have plus BY times 6 meters, and all of that equals 0. Simplifying things down, we'll have a minus 60 kilonewton meters minus 120 kilonewton meters plus BY times 6 meters equals 0. And if we put this to the other side, we have 180 kilonewton meters divided by 6 meters. We're going to end up with BY equals 30 kilonewtons pointing upwards. And sum of the forces in the Y equal to 0. Well, we have a positive AY minus 2 times 30 kilonewtons plus BY, which we just found to be 30 kilonewtons. All of that equals 0. Solving for all of this, we get AY equals 30 kilonewtons pointing up. And again, just a sort of a check of our intuition. Does this make sense? Should we expect no horizontal force. Well, of course, there's only vertical loads applied to this. And then in terms of our vertical reactions, well, we have a symmetric system, so we would expect that we would get a symmetric reaction. And, even so, so it's always good to do that intuition check. But what's also good to do is just a statics check, just to make sure we haven't, accidentally, done a calculation wrong or said or forgot a term somewhere. So that's what a statics check is really good for doing with these determinant systems. So our statics check, we sum moments about A. We're going to sum moments about B, and that has to equal 0. And if 0 equals 0, so basically if all of these elements are in equilibrium, then we know that we've done our statics correctly. So we have minus AY times 6 meters plus 30 kilonewtons times 4 meters, then plus another 30 kilonewtons times 2 meters away, and all of that has to equal 0. AX has no horizontal distance from B, so there's no moment generated there. And we get 30 kilonewton times 6 meters plus 30 times 4 plus 30 times 2. We can factor out the 30, and we have 4 plus 2. It's 6 meters. Sorry, that's a negative there. And we get 30 kilonewtons times 6 meters equals 0. We end up with 0 equal 0. All right, and then so, our statics check is done, and we know that our reactions are correct. So now the next thing to do is find out, what are the internal forces within this frame, and if we know what those internal forces are, then we can plot the bending moment diagram. And just like what we did in the last video, the way that we want to try to determine what are the internal actions, the forces and moments, is we will take some cuts on a free body diagram. So if this is the free body diagram of the entire structure, I'm going to draw 3 different free body diagrams to sort of demonstrate, the principle that we brought up in the last video is that as we are drawing this, we need to keep in mind Newton's third law. And that Newton's third law is that we have equal and opposite reactions. And so as we look around as these forces are trying to go around a corner here, we just basically need to do this bookkeeping exercise in order to make sure that we, if we have a force or a moment which is acting on one portion, that it's acting for an equal magnitude in the opposite direction on the adjacent portion. So we need to draw some free body diagrams in order to understand this structure further. And remember, free body diagrams are there to take a more complicated system or structure and break it down into pieces which we understand. And so I'm going to take 3 different cuts. So my first cut will be just to the left of this column. And it's going to encompass all of the left-hand side. And I'll call that free body diagram 1. Then I'll do another cut, which is just at the joint. And then I'll do finally a third cut, which is just going to be the column. Maybe we'll just call that right-hand side column, RHS. So let's draw these free body diagrams out, and then we can draw them out, and we can use our equilibrium equations in order to find out, well, what are the actions that are interior here. So we'll draw them out first, and then we'll go through, and we'll draw each of them out first, then we'll go through and we will solve these equations. So for free body diagram number 1, which is this left-hand side here. And I'm just going to go through and give the specimen a little bit of a thickness here, just to hopefully help make things make a little bit more sense to you. And my scale is off just a little bit, but that's going to be okay. 30 kilonewtons, 30 kilonewtons. Two meters, 2 meters, 2 meters, and we have a 30 kilonewton force there at the reaction. This is 4 meters tall, and anytime that we make a cut on an element, we expose the internal forces and actions, and so it's going to have some shear force, V. It's going to have some moment. In fact, let's call this VBM for beam, and let's call this moment BM, and it will have some axial force, N beam. And no matter where we take that cut, if we're exposing these internal actions, we're going to have these three, which we have to solve for. And with this free body diagram, we could start solving immediately because we have 3 equations of equilibrium for a 2D system, and we have 3 unknowns. But before we start working into the mathematics, I want to draw the other 2 free body diagrams, mostly to illustrate how these forces are then transferred through to the rest of the structure. So the next element which we will draw will be the free body diagram of the joint. So just this right up here. So with the free body diagram of the joint, we'll draw it again with some thickness. And one of the things to keep in mind with this joint free body diagram is I'm going to assume where I've taken the cut is we are at a infinitesimally small distance, basically 0 away. And so that each of these arms is just 0 meters long. And the reason for that is it helps with the mathematics a bit. And let's also, we can take this free body diagram anywhere we want. What we were trying to find here is, well, what is this moment right at the corner there? And so we're going to draw a free body diagram right at the corner. So the thing to keep in mind, again, we have 2 cuts here, so we will be exposing 2 sets of internal actions. On the beam side, they're going to be the same magnitude as what's in free body diagram 1, but going in the opposite direction. So our shear force of the beam is going up on free body diagram 1. Well, we need an equal and opposite reaction in the other side of it, so it's going to go down on the joint, so you get V beam. The axial load here is going to the right, so it's going to go to the left. So basically make sure that, that we're assuming that this beam is in tension, so we have to assume that that joint, that reaction is also in tension. So opposite direction there. And then our moment is going counterclockwise on free body diagram 1. So it has to go clockwise MBM for the joint. Now, that's only one cut. We have a second cut which we've made. And what I'm going to do is just assume that the internal actions are just going to go opposite of what I've drawn here, which would make sense because this joint also has to be in equilibrium. So we need all the forces and moments to sum up to 0. So we have the shear in the column, V column. We will have the axial load in the column and column. And again, we're going to point it up because that shear force is pointing down. And we will have a moment. And I'm going to make it go counterclockwise and column. Now, another sort of thing to keep in mind and to pay attention to is that when you transfer from a beam into a column, so like what we're doing up here, the shear that is in the beam will become the axial load in the column. And the shear in the column will become the axial load in the beam. And that makes perfect sense if we think about this in terms of equilibrium. And so if you ever get confused, draw yourself a small free body diagram of your joint. And that will always help to illuminate these problems. So we're going to draw this sort of final free body diagram, which is of the right-hand side column. Go free body diagram. And we have the column here, has the cut on top. It is four meters tall. It has a base reaction of 30 kilonewtons pointing upwards, just from this right here. And then we have a cut, so we know we have some internal actions, but these internal actions have to be equal and opposite of what we've put on the joint. And so our axial load for the column, well, we're assuming it's going up to the joint, so it has to go down on the column. And that says that this column would be in compression, which is what we would assume. We've got some load pushing up, well, and then some load pushing up and load pushing down, so that means that we're going to be squashing this column. So again, as you go through this, always try to do a little bit of an intuition check, and does this make physical sense? Our shear on the joint we have going to the right, so on the column, in order to obey Newton's third law, it has to go to the left. And so we have V column. And then our moment, we have it going counterclockwise at the joint, so it would be going clockwise on the column. So that would be M column. Now, we are able to use our equations of equilibrium, and we can start really solving on any of these free body diagrams, because as you can see, they're connected as you go through here. But we're just going to start from the top to the bottom, and we will work our way through. Another note is, because we have a symmetric system, I'm only going to be looking at 1/2. If we had asymmetric loading and the like, well, we could do the same process and then just take another series of cuts. So in order to find out, well, what are these internal actions, and then by those internal actions find out, well, what's the magnitude of the shear force or the bending moment diagram, and then be able to draw our bending moment diagrams and shear force diagrams and axial force diagrams, let's start doing some statics. So the first thing I want to do is let's sum the moments at the cut. I'm doing that because then I'm only dealing with one variable, because the shear force and the axial force have no orthogonal distance, so it sort of cancels those out. So we will start with that. We'll go sum of the moments at the cut equals 0, and we will go as typical with our right hand rule, counterclockwise will be positive. So what do we have? We have M beam, which is positive, and then we subtract out, well, this 30 kilonewton reaction times 6 meters. Then we'll add these two loads. The first one is going to be plus 30 kilonewtons times 4 meters. And then we have 30 kilonewtons times 2 meters away. and all of that has to equal 0. Well, then we have MBM minus 30 kilonewtons times 6, and then, well, if we combine these two, so if we factor out the 30, then it's 4 plus 2, that's going to be 6, so we actually end up plus 30 kilonewtons times 6 meters, and that equals 0, which means that actually our internal moment here at the joint, or just at the face of the joint, MBM equals 0. So we have no moment by the time we get to that joint. So that's interesting. Well, let's look at the other elements that we have. So let's sum the forces in the x direction. And we get NBM, so the axial force in the beam equals 0, because that's the only force in the x direction. And now the only thing we have to find is the shear in the beam. So look, sum of the forces in the y equal to 0. We get 30 kilonewtons minus 2 times 30 kilonewtons. And then finally plus VBM. All of that equals 0. We solve for this. We get the shear force, VBM, equals 30 kilonewtons. All right, well, that's very good. Well, we can apply these to the joint, and we will just continue working through our equilibrium equation. So we will start with summing the forces in the y. And we get minus VBM plus the axial load in the column equals 0. And we get minus 30 kilonewtons plus n column equals 0. The axial force in the column equals 30 kilonewtons in compression. Sum of the forces in the x will equal 0. Again, we have NBM equals 0, and so V column will equal 0. NBM plus V column equals 0, so V column equals 0. And then finally, some of the moments equals 0. You have now again the orthogonal direction where we've taken this free body diagram of the joint basically at the very tip of the joint, so there's no dimensions, so all of these forces have no orthogonal distance, so it's only the moments, and we get MBM equals M column, so moment of the beam equals moment of the column equals 0. Alright, so now time for our final free body diagram in here. We'll put a little bit of a dashed line here just to keep our equations separate for each of these free bodies. Now, the final free body diagram, if we push her up here, well, I know that the moment of the column is 0, and I know the shear of the column is 0, so the only thing we have is the axial load. So let's go sum of the forces, and the y equals 0, minus n column plus 30 kilonewtons equals 0. So the axial load of the column equals 30 kilonewtons in compression. So this final check is essentially like a statics check for us. I mean, this is what we expect. We're getting it from two different free body diagrams using two different methods. The other thing to keep in mind is that here again, the shear in the beam is becoming the axial load in the column, and that makes perfect sense because there's you'd have the, if this was just a simply supported beam like this, or you'd have two reactions just like you have here. And well, essentially all we've done is we've just extended those reactions and turned them into columns. So the load path is that the force has to come down here. Well, that force has to get down to the ground somehow, and it's going to be shear into the beam and turning into axial load into the column here. The other thing which is good to note, so we have a pin here, so we can't generate any moment. And we also have zero moment at the joint. So we should expect, based upon the definition of what shear is a change of moment. Well, if you go from zero moment to zero moment, and we have no forces in between, then we should expect zero shear in our column. And that's exactly what we got, where the column shear equals zero. So now that we know what our internal actions are, we can go ahead and plot our shear, bending, and axial force diagrams. And so I've got them sort of started over here. And what we're going to do is use a combination of what our loads are that we've found and what our internal actions are, as well as the graphical rules which we've learned for going from a free body diagram and the relationship between shear, load, and moment, and how shear is the derivative of moment, and how the load will be the derivative of the shear. So starting with our shear force diagram, in fact, what I might do is I think I can keep these two side by side and just try to get this on camera there for you. There we go, and that gives us an opportunity to see what we have. So for our shear force diagram, let's just put our sign convention in here. Where we're going to have, if the shear makes the element want to spin in the clockwise direction, that is positive. And so while it's the same rotation, we'll draw it as a horizontal member as well, vertical member, I apologize. And the units will be in kilonewtons. Then for our moment, now remember, we will plot the moment on the tension side of the element, so whatever element is in tension, and that's going to be where the tail is for the moment in that element. But we will call positive for when it's a beam is when the compression's on top, and that's going to be kilonewton meters. And then finally our axial force diagram down here. Positive we are going to call tension, and again that's going to be in kilonewtons. So starting with our shear force diagram, now if you remember, we've got, so it's a symmetric system, so the shear force on the end on this side is going to be the same shear force as what's going to be over on the other side, and the shear force in the beam is 30 kilonewtons. So we will start on this side. We know that we got 30 kilonewtons pointing up. So we will draw up. And then because we have no additional loads here, we have, and that the magnitude of the force diagram is going to be the slope of the shear force diagram. So if we have a magnitude of 0, then we know we have a slope of 0. And that means that's a horizontal line. And we're going to go until we hit 2 meters, and we're going to go over. So if we went up 30 kilonewtons of shear, and then we have a load of 30 kilonewtons down, we now have, that's what our shear is. Now, as we go across, again, the magnitude of the force is the negative slope of the line for our shear force diagram. So if we're 0, well, we stay at 0 until we get to our 30 kilonewtons. And it's going to push us down 30 kilonewtons. So I'll put some, it's 30 kilonewtons. and then we will go over also 30 kilonewtons. And the shear directions will look like that. And that's it for the shear force diagram. Because if you recall, we have the shear in the column equals 0. So that's all we need to do. Now, looking at the moment diagram. So for the moment diagram, we know that at the moment of the beam at the joint, we found that equals the same moment as what's in the column, which is 0. So MBM is 0, and then the column moment is 0. So we know that we can start our moment here at 0. And the magnitude of the, if we have a constant, so the magnitude of the shear force diagram will be the slope of the line of our moment diagram. So we know that we've got a shear here, and we have a moment which is going to increase, and we're going to plot on the tension side of the beam. Again, if you think about it, it's the same as the tail side, so the tail side's on the bottom, so we will plot on the bottom, and that's the same. So if you think about the deformed shape, these 2 points are going to really want to make that beam bend in this direction. So we have a constant shear force, which means we will have a linear change in moment. Then we have no shear, and if we have no shear, we have no change of moment. If we have no change in moment, that's equal to a horizontal line, so a constant moment. And then we have the opposite shear, and so we will start going back up, and we'll put a little happy beam sitting there. Now, some interesting things to note here. So when you have this what we call 4-point loading, where you have 2 points pushing down and then you get the 2 points at the reaction. In the middle here, if these two are equal, then we have no shear force and we have a constant moment. So that's can be, we can use that for an advantage where, if we have this beam and we need to say put a hole in it, we might put a hole right here in the middle where the shear force is quite low, and when we take it out of the middle of the beam. You'll learn more about that as we go through this course, but it's just sort of a nice, interesting thing to know. The next thing we need to do for this moment diagram is we need to find out, well, what is this value? Well, the value here is simply going to be this area. And again, this is our, if moment is essentially the integration of shear, well, we can take the area and we can find a value. So this is going to be, and these two are equal, 30 kilonewtons times 2 meters, and that equals 60 kilonewton meters. If you want to prove this to yourself, easiest thing to do is just take a free body diagram right at 2 meters here and just solve for what that internal moment is. Now, the final element that we diagram, which we need to draw, is the axial force diagram. And so this is, again, remember the shear force. If it's in a beam, it's going to turn into axial force in a column. So, and that's exactly what our free body diagrams have shown. And it shows that in both columns we have 30 kilonewtons in compression. So because we are calling tension positive, we will just draw them over on this side here. And because they're both in compression, we will draw them on the same side. And we'll just put a little C for compression, and that's 30 kilonewtons. 30 kilonewtons. So they're nice and symmetrical and constant. So that's a brief overview of how to analyze these systems, when we're looking at a frame, something just slightly more complicated than we have before. Again, the rules for how we approach this are quite straightforward and simple. First thing we do, find our reactions. Then we take some free body diagrams and find our internal actions, our internal forces and moments. So this is our shears, our axial loads and our internal bending moments. And then we can use the rules, we can use those values plus the rules for our relationship between shear and bending moment in order to plot this up. And if ever we don't know what the value is of one of these actions, we can always go back to taking free body diagrams to determine it. So with that, thank you for watching.